Okay. All right. We used up two of our choices for interpolating. There's n polynomials. That is two n choices used up. Now what we're going to do, our next decision that we're going to make is that we want the derivative at xj to match the derivative of xj plus 1 at xj plus 1 to match the derivative of sj at xj plus 1. Think about what this means. Notice the data point is the same. That means that when these two things come together, derivative of possible, the function is continuous and the first derivative is possible. So this means, this condition right here means S, the derivative of our interpolating polynomial, the whole thing is continuous. That's what we're forcing it. This is this choice. Continuous on AB. Continuous. Okay, how many degrees of freedom are we going to need to do that? How many choices does this mount up to? Let's go to our little baby example here. We want the derivative to be matched right here and right here. We have one function, we have P1 and P2, and we want them to have the same derivative right here. Then we have P2 and P3, and we want them to have the same derivative right here. How many choices is that? Yeah. This case, 2, but how many in general? N minus 1, absolutely. I mean, this big example, N is 3, that is N minus 1. Okay, N minus 1. Used up. Okay, then I'm going to insist on another condition, this thing, and that is that the second derivative is matched. So where the functions join on my piecewise function, the function has the same value at that point. The first derivative is the same, and the second derivative is forced to be the same. This is going to be then j equals 0 and minus 2. So the other one, just write that down. Okay. Now we match the first derivative and the second derivative. Same amount of choices are used out of all my choices. And used up. So let's just write down what we know. Sx has 4n degrees of freedom. We have all these cubic polynomials, each with 4 coefficients, pick them however we want. And we have used up 2n of them to make sure it interpolates. We've used up n minus 1 of them to make sure that the first derivative matches. We've used up another n minus 1 to make sure that the second derivative matches. So we have used up is 2n plus n minus 1 plus n minus 1. That is 4n minus 2. So we have 2 more choices left. There are 2 choices left. Okay. That is 4n minus 2. That's 2. Okay, so we have several choices on how to do this. What to do with the remaining 2 degrees of freedom. I don't have that. There, this one. Okay, I'm just going to write this. This is point number 7. Just like that. what to do with the remaining two degrees of freedom. What we're gonna do is we're gonna talk about what happens at this left and right hand point of the whole interval, x naught and x n. So there's going to be three choices of what we're going to do. We're going to say that the second derivative at x naught is equal to the second derivative at, well, they're both going to be zero. No conditions on the direction of one point. Well, that means the curve just takes a straight line after the first and last interpolation. That's what we call natural evaluation. I have, in fact, a few people that have it. Now, if I go with the first condition, so it's into the endpoint, that is so that I need to do another one here. I'll go with that. What is your vote? Let me do this one down here. I'm going to be in something that this one down like that. There. What happens after the endpoint? What is that? Natural or three the boundary condition. If you want to match, we're going to interpolate. I'm interpolating these points like this. And again, I brought this example that I made myself, which show you, but it was actually sort of maybe possibly surprising, I don't know, is that this is actually not the confusing thing to look like. But this is right? Anyway, let's just go. It's a highly exciting feature. Let me just get to where I can say a bit more about that. So this is no condition imposed. We just the second derivative to be zero. No condition imposed. The second derivative is zero means the first derivative is a constant. Means you got a lot. So it takes a straight line. That's option one. Two choices. Our last two degrees of freedom. Next choice is to match the derivative. The derivative of the polynomial to the derivative of the function at the leftmost endpoint, and to match the derivative at the rightmost endpoint to the derivative of the function at the rightmost endpoint. Okay, that forces this line to take a specific direction at the endpoint. This is not as useful of a choice in the sense that you now need to know the derivative at your interpolating points. You may not know that, right? So that's a bit of a bummer. This one is easier. Okay, so that's the next possibility. The other one is to, it's called not or not condition. That is to ask that the derivative of your leftmost polynomial at the third derivative at your first point is, this is imposing a condition only on the first polynomial that you've concocted and the last polynomial. This is your other possibility. This is the other common possibility. You also don't need to know the derivative. You don't need to know the derivative of the function. Third derivative of a constant, the third derivative of a constant. And this will make the third derivative continuous at x1 and x minus 1. Called this way because in effect what's happening, because you're at a cubic and you're matching the third derivative, in effect that point is that's the point from the word. The surface smoothly goes right through it. It's called mathematics. Okay. Out of these three possibilities, A is the simplest. B is the most accurate, but you have to know the derivative of your function. And C is equivalent to using a single cubic polynomial in the first and last two intervals. C is commonly used in software. This one is commonly used. Okay. Let's just take a we have 5 minutes. Great. We can take a look at some features of the cubic spline. I think my picture will come magically. It will not. Just for the record, at my last lecture hall, it said that the IT services room flooded, and they're having problems with internet connectivity as a result. I think that might be a portion of what's wrong here. Not able to download this properly. Okay, let me just draw the picture that you may have in front of you, and this is the shipbuilding. So when you're building a ship, you have the situation where you have pieces of wood. You have along the sides of the ship, first pieces of wood, and so you have an architectural drawing of what you want, some curved piece of wood. Okay? And meanwhile, you want to transfer that onto the actual piece of wood that you cut. So what you do is you put your previously straight piece of wood. Maybe you wet it or you make it quite thin, the veneer of some sort, but whatever, you make it so that, or you have enough force so that it is pliable, and then you hang these little weights on it, like that, until this thing moves down and is sitting on the curve, and then you hang another little weight. These are like you're interpolating those, and you bend this down like that, hanging weights on here until the thing is bent. That is exactly a cubic spline. And then the reason for that is we're not going to go through the derivation of this, but that this is exactly the same as that was hanging weight and hanging weight instead of position. What the shipbuilders do. It is exactly the cubic spline, and that the reason for that is because the cubic spline minimizes strain energy. So this is a physics thing. I'm not going to test you. I'll ask you to repeat what this is, but the idea is what you want to realize is that physically this is a certain type of function, and in fact, this idea, this strain energy is this guy here. Amongst all C2 curves. So what does this mean? So it I have some data points. And I have a piece of flexible function about it. And I ask you, put that flexible function about it through these curves in a way that minimizes the strain energy of all possible functions that are C2 continuous. That is, where the first and second derivatives are continuous. What function am I? This is I think, a different way of asking for a function than you are used to, right? I can just give you a completely different kind of example. I have a ball that's right here, sitting like that. And then I have a table down over here. And I want the ball. I want to let go of the ball. And I want it to land on the table. Right? And I ask you, what kind of ramp should I put here? What type of ramp should I put there so that the ball lands on the table? What type of ramp should I put here so the ball gets down to the table? That's a big change of mindset, right? This is, once you start down this path, you end up in the calculus of variation. And what function do I choose? Minimize and maximize something, not minimize function, maximize function. Okay, so this cubic spline is something that minimizes the strain energy. And we are out of time, which is somewhat of a feature because we'll be back on Wednesday and we actually go to the next constructing energy mathematically. Second here.